equation. Today we have to deal with its application, right? Application of Bernoulli's equations. There are innumerable number of applications. Application of Bernoulli's equation. First important is Torricelli's theorem. What is Torricelli's theorem? This is capital A and this is small a. This height of the liquid is capital H. I am interested in the force exerted and I am interested in velocity of the fluid flux. The velocity with which fluid is coming out. Now, if you take a streamline like this, you apply streamline to point 1 and point 2. You will apply Bernoulli's equation to 2 points on the same streamline. Right? Your Bernoulli's equation was P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. Come in. Today we decided we'll collect 5 rupees from people who come 5 minutes late, 10 rupees from people who come 10 minutes late. You crossed 10 minutes, so your fine is 15 rupees. 1 5. He's seeing cash already. Yeah. 15 rupees. Today people who are coming late, every 5 minutes we are adding 5 rupees. You crossed 10. So your fine is 15 rupees. His fine is 5 rupees. His fine is 15 rupees. Her fine is 10 rupees. He 10 rupees. Yours is 5? Okay. Remember your amount, don't forget. Yours is 15. Depending on the amount of the cash we collect, we will decide what to treat ourselves with. Now, listen, this application is important. You are applying Bernoulli's equation to 2 points on the same streamline. Now, this is open to air, so P1 will be atmospheric pressure. Here, in this derivation, you are given A is much greater than small a. Please listen to the approximation, it's important. If this approximation is not valid, then you cannot directly apply Torricelli's theorem. If this approximation is not valid, right, though always search for this approximation in the question. So, if capital A is much greater, V1 is much lesser than V2. Simply because capital A into V1 is small a into V2. Right? So, this will be negligibly small. Rho G capital H. P2 is also open to atmosphere plus half rho V square plus 0. You are taking that as the reference line. So P0 gets cancelled, rho gets cancelled, V is root over of 2GH. Something very interesting to note that it is nothing but a free fall. Obviously, it will be like a free fall of a body because Bernoulli's equation is a consequence of conservation of energy, isn't it? So it must be a free fall. Now, observe things carefully. Suppose this height is small h. Accordingly, you will have velocity as root over of 2gh. What will be the range? The range will be capital H minus small h is half gt square. This height will be capital H minus small h. This is capital H minus small h, half gt square. R is equal to root over of 2gh into time of flight. Right? From here, how do I get time of flight? Root over of 2 times h minus h by g. So this will be root over of 2gh into root over of 2 times h minus h by g. This will be the range. Is my simplification correct? In the horizontal direction, it is velocity into time. Vertical direction, initial velocity is 0. So h minus h will be half gt square. Now this is the range of the liquid which is coming out of the flex, right? Now if I want this range to be maximum, so this what will I do? Root 2 into root 2 is 2 root over of h minus h into small h. Root g will get cancelled out. For r to be maximum, dr by dh should be 0. At what height should I pin a hole so that the range is maximum? If I differentiate this, I'll first square it 4 times hh minus h square. So 2r dr by dh chain rule I applied 4 times capital H minus 2h. This will be 0. That implies h is equal to h by 2. Are you trying to tell me that for the range to be maximum, the height at which I should pin a hole is h by 2? Sir, this doesn't make sense, sir. Please pull it down as much as possible because the velocity will increase, but then time of fall also will decrease. Just velocity increasing doesn't help. Time of fall also should be maximum. If I am going up, time of fall is increasing but velocity is decreasing. If I am going down, velocity is increasing but time of fall is decreasing. So are you able to intuitively feel that the maximum range will come when you pin a hole at the center? You are trying to tell me that if this is a container filled with liquid, range will be maximum when this is h by 2 and h by 2. This is h by 2 and this is h by 2. Implies you are leading me into a new argument. That means if I go above or below, range will decrease. Am I right? Range is maximum at a height of h by 2. So if I go above or below, the range will decrease. That means there will be a point above and below for which the range is the same. There will be a point above and below for which the range will be the same. Quite obvious. I am able to see that. Interchange these both. Range is 2 times root over of h minus h into h implies, have a look, if this is h and this is h minus h, you will have range here. Vice versa, this is h minus h and this is h, you will have the same range. So implies small h from above and small h from below will give me the same range. Implies small h from above and small h from below will give me the. Is the logic clear to all? Torricelli's theorem. Velocity of the liquid will be root over of 2gh. H will be the height of the liquid column. Remaining is mere kinematics. Am I expected to remember the expression for range? Yes, this expression for range is mandatory. At what height will range be maximum and at which two heights will range be the same? You are expected to remember these results. What if they give a container like this? Whatever is the height of the liquid column h, you will take root over of 2gh, no doubt. But it will go as a projectile like this. Theta, range, all formulas of projectiles will apply here. Root over of 2gh. Velocity will be root over of 2gh because you are getting velocity using conservation of energy. You are getting velocity using conservation of energy. Energy doesn't have direction. So velocity will be root over of tgh, but thereafter the range will follow all the norms. What if the container has a hole underneath? Matters not. This will also velocity be root over of 2gh. Instead of hole on the side, you can have hole underneath. It doesn't matter. It will be under root 2gh. It will in any direction. You have this. Suppose I have got this as small a and I have got height to be capital H. The velocity is root over of 2g capital H with respect to the container. So thrust force will be equal to Vr dm by dt. In the case of a fluid, Vr dm is a rho dx by dt. A is the area of cross section, dx, a dx into rho, a into dx, area of cross section into length dx will be the volume, volume into density will be the mass, dx by dt will be Vr, a rho Vr square will be the thrust force on the container. They will even ask you what will be the initial acceleration. You know the thrust force, you know the mass, should not be difficult for you at any stage. Vr dm by dt in variable mass, do you people remember? Variable mass. Velocity at that instant is Vr, root over of 2gh. You will put root over of 2gh. As height decreases, velocity changes. So you can tell me at one particular instance only. Rho into area of cross section into VR square. Now, what if I consider a container, either I have a hole to the right or bottom? We don't mind either way. This is capital A. The height of the container is capital H. How much time does it take for it to get emptied? How much time does it take for it to get emptied? You are given capital A is much greater than small a. Capital A is much greater than small a. Right? You are given this. Capital A is much greater than small a. That means velocity will be root over of 2gh. Now there is a basic doubt that the students get. If capital A is much greater than small a, that means this velocity you are taking is negligible. That was what you did in the Bernoulli's equation. So it will never get emptied. So this is the logic which students apply. We consider after time t in a short time interval dt, let this height be y, and in a short time interval dt this moves by a distance of dy. Torricelli's theorem of root over of 2gh is applicable only if the velocity of the upper layer is negligible. But A1 V1 equal to A2 V2 is universally applicable. Time taken to empty the tank. Now capital A into minus dy by dt, A1 V1 is small a into root over of 2gy. I used A1 V1 equal to A2 V2. Who gave you the permission? That is always applicable when the density will remain constant. Density is constant, right? So A1 V1 equal to A2 V2. But something more interesting here. How can you use Torricelli's theorem here? In a short time interval dt, this did not appreciably move. Dy is limit delta y tending to 0. So I could use Torricelli's theorem in that short time interval dt. Is that clear? So dy by root y is a under root 2g dt by capital A with a negative sign. Time t equal to 0, y is h. Time t equal to t naught, y will be 0. They can ask you time taken for it to come to half the height, 3/4 height, so on and so forth. Yes or no? I am finding the time for which y becomes 0. They can ask you time taken for the container to empty 1/4, 3/4, so on and so forth. You will complete the simplification, don't leave it here. Find out the time taken for the container to empty.
The velocity of the liquid is uniform. Uniform. Like until it reaches the belly water.
I said something here which you missed. In the short time interval dt, y remains. Only then I can write here root over of 2gy. The moment y changes, this will not be uniform. In that short time interval, velocity can be assumed to be root over of 2gy. You should tell me why is it negative. Y is decreasing, dy by dt will be negative. Yes or no? Two other applications of, did you complete the integration?
Yes, sir.
Two other applications of this. Venturi meter. Nowadays, all these equipments are completely replaced. Nowadays, you have got sensors which will tell you the fluid flow in the tubes. This is capital A, this is small a. Here velocity is V1, here velocity is V2. Just imagine, this is static pressure, this is dynamic pressure. Fluid is flowing in this direction, right? But from this side, if I calculate the pressure, it will be static pressure. AV1 is equal to AV2, first equation. Are you people okay with that? All I need to do is to calculate the velocity of the fluid flow. Capital A is greater, so V1 will be lesser. V1 is lesser implies pressure will be greater. I'll consider this to be H1, this to be H2. See, the difference between these 2 points is almost negligible. I'll take this as point 1, I'll take this as point 2. So, gravitational potential energy difference is negligible, right? It's the same Venturi meter. So, that you may ask, you are taking the pressure here, but don't you think you'll have to take here? This is negligible, right? So here velocity, area is greater, velocity is lesser. Velocity is lesser, pressure will be greater. Bernoulli's equation P plus half rho V square is constant. At the same height, potential energy will be the same. P plus half rho V square is constant. Hope you people remember. Now, in this particular case, when I apply pressure here, P1 plus half rho V1 square is P2 plus half rho V2 square. This is my second equation. Why are you not taking rho GH? Both the points are at the same height from the ground, right? P1 will be H1 rho G, P0 plus H1 rho G half rho V1 square, P0 plus H2 rho G plus half rho V2 square. P0 will go, density gets cancelled, H1G plus V1 square by 2 is H2G plus V2 square by 2. This is my second equation. First equation is AV1 is equal to AV2. Venturi meter is generally used to measure the value of V1, velocity at 1. So eliminate V2. How do I do that? H1G plus V1 square by 2 is equal to H2G plus V2 is AV1 by small a with a 2 here, whole square by 2. How much is V2? A V1 by small a. V2 square A V1 by small a whole square by 2. Multiply all throughout by 2. 2GH1 plus V1 square. 2GH2 plus A by A whole square V1 square. Take this to the right. 2GH1 minus H2 should be equal to a by a whole square minus 1 v1 square. V1 is, if I tell you that this difference in height is h, difference in height, root over of 2gh upon a square by a square minus 1. Is my simplification correct? Right? H is the height difference between the two liquid columns in the Venturi meter. H1 minus H2. Quite a few times we write this as A1 and A2. This is the way you used to find out the velocity of the fluid flow in a pipe. Right? Velocity of the fluid flow in a pipe. But now this is extinct, completely extinct. Now they have got sensors fit at every point in the water pipelines. It will tell you the fluid flow, what just fluid flow. It will give you information about the temperature of the water, pressure there, and as well as the purity of the water levels there. Now they have got a panel of sensors fit there. They fix a panel. One will give you pressure, one will give you velocity, one will give you purity. Temperature of water also is measured there. This gives you only velocity. And manually you will have to go place, measure the height and do that. Sensors will tell you the velocity all throughout the pipeline. Sitting in the control room, you get all the information. Where the pipeline bursts also, they will have information. Before the local people realize what is happening, they have the information. Just that they don't act so quickly is a different issue. Huh? Pardon? Let's give them surplus time. Only one approximation. Point 1 and point 2 are at the same height from the ground. Technically, point 1 is here. So, when I take gravitational potential energy, point 1 will be slightly above point 2. But this height will be some 10 meters. and this will be in few centimeters. So I'll assume 1 and 2 to be at the same height for gravitational potential.
Sir, after I there is no
Venturi meter, VENTURI,
sir.
VENTURI. There is no E, it seems. Right. Thanks for enlightening us, but you will pay a fine of 10 bucks today.
Why?
My wish.
Sir, I did nothing wrong.
When did I say that fine is paid only if you do something wrong? Right?
So I am poor.
For 10 rupees. Am I blocking any of your view?
Sir, 10 bucks is 800 more.
No, 10 bucks right now is 10 bucks, 10 rupees. You pay me 5 years down the lane, it will become 10 US dollars. Pardon? That you will have to bargain with him. I will not demand. You convince him, I don't mind. Am I blocking your view? And stand up, you will be able to see the boat. I. Come again? Simple. A1 V1 equal to A2 V2 is conservation of mass. Conservation of energy, Bernoulli's equation. Now suppose you speak about the pipette's tube. This is also extinct now. Pipette's tube. Here spelling is correct. Right. I saved you 10 rupees. This is the fluid flow. This is the fluid flow. Because of the fluid flow, here you will take this as point A. There is certain height to which the liquid level rises. The other tube is kept this way. And they make the nozzle very small. They make this nozzle very small. So velocity of the fluid flow there is almost negligibly small. This velocity will become almost to zero. So the height to which the liquid level rises here will be greater. The difference will be h. This is h1. This is h2. h2 minus h1 will be h. Why will it rise to a greater height? Observe this. Velocity becomes zero. Lesser the velocity, greater the pressure. Greater the pressure implies it will go to a greater height. So now you are applying Bernoulli's equation to A and B. PA plus half rho VA square is equal to PB plus half rho VB square. Why are you not taking potential energy? Both the points are at the same height from the ground. Right? VB is almost tending to 0. So your requirement is VA. PB minus PA. PB minus PA 2 times divided by rho square root will be the velocity of the fluid flow using pipette's tube. Same pipette's tube for gases. For gases, you let the gas pass through the chamber and you will use a manometer type structure here, and you will fill that with mercury. Here again it goes the same way, and the nozzle will be small. Here the nozzle will be small. Have a look at it. This is point A. This is point B. Technically, this height, watch out for it. Then you have mercury trapped here. Manometer, mercury trapped here. Here velocity will be greater, pressure will be lesser, so it will press the liquid to a lesser height. Here velocity will be lesser, pressure will be greater, it will press the liquid down. The difference in the heights is h. I repeat, here velocity is lesser, pressure will be greater. Greater the pressure, it will press the mercury down. Right? Contrary, here velocity is greater, lesser the pressure. Mercury will be at a greater height than this. Now you write the equation PA plus half rho VA square should be equal to PB plus kinetic energy here is 0. Now VA square is equal to PB minus PA 2 times divided by rho whole to the power half. Now why are you leaving PB minus PA this way? PB minus PA will be H rho G, but rho will be the density of mercury. I will not write that rho here. That rho and this rho you cancel out. This rho is the density of the gas. PB minus PA, when you substitute difference as H rho G, that H rho G will be the density of, say here I don't have that problem. Here PB minus PA is the same fluid rising up. Here I don't have the issue, but here when I write PB minus PA, PB minus PA will be H rho of Hg into G. That rho and this rho are not the same. Keep that in mind. Both are extinct pieces, but you have it in your syllabus. You close the nozzle this way, the velocity will become negligible. You want it in the swing mode or should I keep it above? Hmm. We can
Can we take rho from the first place? PAP from that we take rho.
you take rho.
CP and PA are equal to rho G H1 and rho G2. So can we take the rho from that to take the same?
Yeah, we can. That's what I told you. Rho is the same here. There it's not the same. Now listen. The fluid is flowing this way. You keep a pipe like this, right? This is of height h naught. This is y inside the liquid. To what height will the fluid rise? To what height will the fluid rise? If the velocity of the fluid here is v, find h. Find h. To what height will the fluid rise? Stop staring at me and start solving. Cross sectional area of the pipe is constant. Initial pressure, that will be P naught plus rho gy to a depth of y, right? Here, take this as point 1, take this as point 2. Generally, students tell me they are comfortable taking this as point 2. They'll find out the velocity here. With that velocity to what height it goes, they'll be able to calculate. This is what they're comfortable with. I would suggest, who is asking you the velocity here? Nobody is asking you the velocity here. Directly take this point 2 and apply. It's the same streamline, right? So it is P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho GH2. P1 is P0 plus rho GY. See if you are convinced. P0 plus H rho G, technically Y rho G. V1 half rho V square. This will be 0 because you are taking this as the reference line. Height of that is the reference line. Topmost point P2 is atmospheric pressure. Velocity will be 0. Rho G H naught H plus H naught plus Y. H plus H naught plus Y. See if you are convinced. If you are taking this as the reference line, potential energy here will be H plus rho G H plus H naught plus Y. P naught gets cancelled, right? Rho gets cancelled. Yg plus V square by 2 is H G plus H naught G plus Yg. Yg gets cancelled. Your requirement is height H. V square by 2 minus H naught. V square by 2G minus H naught is the height to which the liquid level rises.
For P pressure and volume, you are taking P0 plus Y over
This is the liquid level. I introduced a pipe this way, right? The pipe goes out. So this is the liquid level. The pipe is this way. So what will be the pressure here? P0 plus Y rho G. Here what will be the pressure at 1? P0 plus Y rho G. Here I cannot take Y rho G plus H naught rho G simply because here fluid is flowing. I cannot take static pressure. In this direction here I can take static pressure. This is open space. Atmospheric pressure plus Y rho G will be the pressure here. You mean here? Here.
Sir, that's a pipe.
This is a pipe.
Yeah.
हाँ.
So the fluid is
Let it flow. दिक्कत क्या है? What is the problem?
sir, you just now said you are not taking H naught because the fluid is flowing.
Oh God. Turn the page. Venturimeter. Have a look. The fluid is flowing here. If I am calculating pressure from this side, what will I do?
Yes, sir, but here it is, we can take it as stationary because it will stop at a point. It
Right.
can only go.
Apply the same. In this, the pipe, the fluid is flowing. I cannot use H rho G. But this side, fluid is flowing this way. If I am calculating pressure from this side, why will I not use H rho G? This side is at rest. Fluid is flowing this way. So if I am calculating pressure from the top, H rho G, below 2, here pressure will be P naught but not here. Here fluid is flowing.
So at that point, it below 2.
All throughout the pressure will be P naught. P naught in the air. In the fluid, no.
So
Pressure will be P naught only here outside.
Sir, just where the tube ends the machine.
No, their pressure in air it will be P naught. In the fluid, for example, if you take a water pipeline like this, water is flowing like this. Pressure here and pressure here will not be the same. Pressure at one is not equal to pressure at two. It's open to air, no air. In air it will be atmospheric pressure, not in the fluid.
Something similar to that. How is P not in the pipe now? How is that pressure lost?
Where did we take P naught in the pipe?
Equation P not is P not plus Y.
Huh. We calculated the pressure at 1. Here, this height is Y. P naught plus Y rho G. What is the point? Pipe is not open to air. You are telling me in a container, if I want the pressure here, this point is not open to the air. So I will take only H rho G as the pressure here or P naught plus H rho G. This point is not open to the air. Shall I say only H rho G is the pressure?
Because the pressure of the air acting on the surface is an
Can I rub the board? Only one sincere student. तारीफ करो क्या उसकी अरे यार Now, two typical structured problems from Irido. This liquid container is rotated with an angular velocity omega. This is open to air. The length of the liquid column is L. Length of the tube is L. Right? The liquid column's length is H. There is a small tiny hole here. The tube is rotated with an angular velocity omega. Iridov is asking about the axis O dash. Velocity of the fluid relative to the tube. Velocity of fluid relative to tube. Velocity of the fluid relative to the tube. Now select one point here and another point here too. Select one point here and another point two here. Now you basically apply Bernoulli's equation. Here relative to the tube, recollect, relative to the tube. Tube may be rotating with certain velocity. You are finding out velocity relative to the tube. Bernoulli's equation will give you velocity with respect to the container. Container is at rest, we are on the safe side. Even if not, you will get velocity VR. This root over of 2gh in Torricelli's theorem. This root over of 2gh is basically with respect to the container, not with respect to the ground. Luckily for you, container is at rest, so you are assuming the velocity to be with respect to the ground. But if the container is moving, root over of 2gh is with respect to the container. Recollect, you selected one point here and one point here and you applied Bernoulli's equation. So the velocity is with respect to the fluid or the container. Now you selected one point inside, one point outside. P1 plus half rho V1 square is P2 plus half rho V2 square. Why are you not taking gravitational potential energy? Same height. P2 I can take as P0, V1 I can take as 0. Listen, this area of cross section is large when compared to this. It is at rest inside the container. Alright, tube is rotating, no sir. Tube may be rotating. Velocity of the liquid with respect to the container is 0. Right? P1 minus P0 half rho V square. V will be the velocity of the fluid at that particular point. Now consider one step. An element dx at a distance of x. An element dx at a distance of x. dp into area of cross section provides the required centripetal force. dm omega square x. Yes or no? This dm will be area of cross section into dx into rho omega square x. dp into a will go. dp is rho omega square integral x dx. Pressure difference, right? You are going from L minus H to L. Least value of x is L minus H. Maximum value of x is L. Pressure, you are going from P naught to P1 at L minus H. This is open to air. When it is open to air, all throughout here you have got air. Then at L minus H, pressure will be P naught. At L, the pressure will be P1. P1 minus P naught rho omega square L square minus L minus H whole square by 2. This is my first equation. This is my second equation. Equate both of them. Half rho V square is rho omega square by 2. L square minus L square minus H square plus 2LH. 2 and 2 half rho V square, and this I equated. 2 and 2 will go, rho and rho will go. V square is omega square into 2LH minus H square. V will be square root of this. This is the velocity of the fluid with respect to the container. A typical problem from Meredov which becomes standardized theory. Understand two things. Firstly, you found out the pressure difference between these 2 points using Bernoulli's equation. Technically, you found out the pressure difference between 1 and 2, but incidentally, pressure at 2 and pressure here will be the same because they are open to air. Right? In days to come, can you make a guess what we will do with in heat and thermodynamics? Here, we will close this. So what happens? The gas inside is trapped. You will apply P1 V1 equal to P2 V2 to the gas trapped inside. Initially, when it was not rotating, pressure was P1. Now when it is rotating, pressure is P2. Now when it is rotating, what will volume be? L minus H into area of cross section. Is that clear? Yes or no? So right now this is open to air. That means the pressure here is atmospheric pressure. The pressure here is also atmospheric. Very good. You will have 15 minutes of a break. You have 15 minutes of a break. Hmm? No. We'll be done with fluids today. I'm coming back on 10th. And then we'll complete waves. Right? 2 days for transverse waves, 2 days for longitudinal waves. I'll be arriving on 10th probably. 11th. 11th से भी 11th class. Pause. Now, one of the most important application of Bernoulli's effect is siphon tube. Siphon tube. You take a tube, dip it one side in the fluid and keep the other side down. Fluid on its own will not rise up and come down. Why will the fluid rise up and come down? It will not. But suppose I fill the tube with the same liquid and then I dip it. Fill the tube with the liquid, dip one side here and the other side. Only condition is I should keep this end below this. Below this level. If I keep it below that level, the fluid will keep flowing. Once upon a time, today all the vehicles have got equipments where you cannot steal petrol easily. Once upon a time, they used to open the scooter knob, put a pipe inside, you take the other end of the pipe. How do you fill it? You suck air out of the pipe. Only trouble, petrol should not enter your mouth. The moment you see the taste, you'll have to spit it. Hold this and keep the pipe down. You will be emptying that particular tank. Purely a direct application of siphon's tube. Listen to the condition. If this point is above this, the fluid will not flow. This point is below this, the fluid will flow. How is that possible? How do you prove it? Watch out for it. You take this reference line to be D. This pipe is inside. You have taken this point as 1, this point as 2. You are calling this as A. You are applying Bernoulli's equation at 1. P1 plus half rho V1 square plus rho Gy. You are taking this as the reference line. So this will be a right of rho Gy will be P2 plus half rho V2 square plus rho Gy2, which will be 0. You are taking this as the reference line. So this will be Y. Both of them are open to air. This is also P naught. This is also P naught. Half rho V1 square plus rho Gy is half rho V2 square. Rho gets cancelled. Right? Now understand one thing. This area of cross section capital A is much greater than small a. Capital A is much greater than small a. So V1 will tend to be 0. V1 will be 0. And hence you will get V2 is equal to root over of 2G by something that something that we were expecting. No big deal. So when will V2 become 0? V2 will become 0 if y is 0. The difference between this height and this height. By any chance, if this goes above this, the fluid will go back into this liquid. It should be below this reference line. If this end is kept above, the fluid will go back. Keep it below, the fluid will keep flowing. Greater the value of y, greater the value of the velocity. Now, afflux of speed at A, observe this. Fluid speed Fluid speed at A is of interest for us. How will you apply that Bernoulli's equation? PA plus half rho VA square plus rho GYA will be equal to P2 plus half rho V2 square plus rho GY2. This will be 0. You are taking this as the reference line, right? PA plus half rho V square plus rho G y plus h. You are taking this as the reference line. What is this particular point? You took this as h, this as y. So rho G y plus h will be equal to P naught plus half rho V2 square. Now listen carefully. Area of cross section here and here is the same. So A1 V1 will be equal to A2 V2. Velocity at those 2 points will be the same. PA plus rho G y plus H is equal to P naught. So pressure at A is equal to P naught minus rho G y plus H. Why are you so keen on telling us the pressure at A? You are keen on telling me the pressure at A because have a look at it. The pressure here is P naught. Pressure here is P naught. So the pressure here will be P naught. Pressure at A is lesser than P naught. So now you understand why the fluid is flowing. So pressure at A will be lesser than P naught. Hence the fluid is flowing till here. Once it comes to here, by default it will go down. Why the fluid is rising and flowing ka justification, that is. Here I am not interested in the justification, I am only interested in the velocity. But why should the fluid flow? If initially there was no fluid, you cannot apply Bernoulli's equation. Now that you have fluid filled inside this, you will have a particular point here in the fluid and a point here in the fluid and a point here in the fluid for which you can apply Bernoulli's equation. Right? So the second part is the justification as to why pressure at A, this A and this A are not the same. This area of cross section, pressure at A is lesser than atmospheric pressure. So this will push the liquid this way and by default it will keep coming out. If we have a pipe, we can demonstrate this. Any form of a small pipe, 2 mugs of water and a pipe, we can directly demonstrate this. This I demonstrate in Mumbai. I don't know how to get a pipe here. I also have one in Mumbai. Let's send him home then. It will pull back. If this particular point rises about this, the liquid will come back here. Y is 0. If y is 0, V2 is 0. If this is kept at this particular level, there will be fluid inside, but it will not flow. Either way, if you keep exactly at the same level, either side it will not flow. and that's static. If I listen all of you, if I keep this point here, the fluid will not be flowing. What is the justification? From this side I told you y is 0. Look at from that side, y becomes 0. P naught minus rho gh, P naught minus rho gh. That will be the pressure for static liquid. So the liquid is static. Fluid will not flow if this particular point is kept here. Understand this derivation carefully, it's important.
So the reason this works because the fluid is
Right. Pressure at A will be lesser than the pressure on the surface of the liquid.
fraction of molecules. So what does this come out? This is fraction of so this how we think it's the dynamics that are the form this is the derivation of the but if you want to find average speed, how do you between Q and integration of this is zero. All the entire thing total speed of all particles divided by and then once we get this and divide it by and we will check the that is how we get this eta. But yeah, I don't so that
Can I rub the board?
Here, we said that the pressure here is P naught, atmospheric pressure because it's open to it. The fluid is flowing.
We are not taking the point inside the fluid. We are taking the. See, once the fluid is out, you can take the pressure to be atmospheric pressure.
Okay, but here Here we are not.
Here, even if you do, you'll get the answer. See, suppose you take the pressure here as P naught. Don't
Yeah.
take here. Here,
Yeah.
when it is open to air,
Yes.
right?
Yes, sir.
You take pressure P naught and solve. You will get V. You will get the velocity. With that velocity, calculate the height. You will get the same answer.
Okay.
V square by 2. If you are opening this to air, right? At the point where it is opening, you can take a point. Now it so happens that that point will be either in the air or in the fluid. It turns out to be the same. If see fluid is flowing this way, I take the pressure here and here. By definition, pressure here need not be equal to the pressure here. But if the fluid is neither bulging this way nor bulging inwards, then that means pressure here and pressure here will be equal. That's what you have to
Okay.
right? By definition, when hey, by definition, when the fluid is flowing, by definition, when the fluid is flowing, you don't take the pressure inside and outside to be the same. But if the fluid is not bulging, then you can take the pressure inside and outside to be the same. So here also, if you take pressure P naught, you will get the answer. Take and see, put the equation. Try. Ah. Velocity of half rho V A square. A1 V1 equal to A2 V2, area of cross section is the same, so velocity is the same. So half rho Va square, half rho V2 square will be equal. One second. This is of density rho to rho. This is of height h. This is of height h. This is V. Small hole is punched to a depth of 3h by 2. To a depth of 3h by 2. That means this is h by 2. Find the velocity of the flux from the hole. Find velocity of a flux from the hole. You can select one point here, one point here, or you can select one point here, one point here. Any 2 points of your choice. Let me select pressure at 1 plus half rho V1 square is pressure at 2 plus half rho V2 square. Both are at the same height from the ground, but then have a look at it. Pressure at 1 will be P naught plus H rho G plus H by 2 rho into G. Pressure at 1 atmospheric pressure plus H rho G plus H by 2 into 2 rho into G plus area of cross section is large when compared to this, which has been told, which I forgot to tell you people, and you people did not ask. Why did you take without I telling you? If you take, I'll ask you why did you take. If you didn't take, I'll ask you why didn't you take the standard assumption. Either way, you're at the receiving end. Pressure at 2 will be atmospheric pressure plus half rho V square. Technically, this will not be rho, it will be 2 rho because the fluid which is coming out is of density 2 rho. P naught will go 2H rho G is equal to rho V square. V is equal to root over of 2GH. 2GH. H का value is given. No. Answer is root over of 2GH. Somebody can take this particular point. It's the same streamline. Take this point and apply Bernoulli's equation. You will get the same answer.
Because it's 4, it's zero, not 2. Because I have much better mark.
What is he saying? I didn't get that.
Because it's get 2x plus half rho square.
Half and 2. 2 and 2 I cancelled it. That's not 2 square. It's 2. It collides, man. If it is liquid is coming from inside that you all of you listen once. These people are repeatedly asking me the same thing. If there is a pipe like this, right? This is capital A, this is small a. Fluid is flowing this way. This is V1 and V2. V2 is greater than, no doubt. But what if fluid is entering in like this? It will collide with the walls, right? So once it collides, its velocity will be lesser. You are decreasing the velocity to zero. When you make the nozzle small, the velocity of the fluid entering in is negligible, right? So they make the nozzle less to make the velocity almost negligible. No, 11 meters per second. Y is 0. If Y is 0, if I bring this here at the same level as that of this.
So why is this?
Arey yaar, diagram from the board you copy it wrong here and you have committed blunder which this is the level of the which is the level of the liquid in the container.
This.
Then it's right. Then draw that properly. Where is that line? Now if I make Y 0, that means this is at the same level from here.
Yes.
Y 0 means it will be P naught minus rho GH.
Yes.
PA is P naught minus rho GH. It's static pressure. Here when you apply, say take 1 and 2. I am taking 1 and 2. Pressure at 1 plus half rho V1 square is pressure at 2 plus half rho V2 square. Always I am preferably trying to select 2 points here. You can take 1 point here, no sir. You can, nothing wrong. Just that potential energy expression I conveniently cancel out here. Right? You can conveniently take that, we have no issue with that. Pressure at 1 will be atmospheric pressure plus how much is this weight? 50 G divided by area of cross section 1 meter square. This will be the pressure here because of the liquid plus half rho V1 square will be 0 because small a is very small. Then why did he give you capital A? For us to calculate this pressure, P2 will be atmospheric pressure plus half rho V square. Atmospheric pressure goes, right? V square is equal to root over of 100 into 10 divided by rho.
So, sir, you are pretty high. Exclude the height. Six floor.
Where did I miss?
Sir, the pressure is P1. You have to take exclude the
I missed that. Right? Plus, how much is this height? 6 rho g. My bad. So now P naught goes, rho will exist, V square is equal to 12 rho g plus 100 g by rho. V will be square root of this. Am I right? This will be 12 g 120 plus 1 root over of 121 is how much? 11 meters per second. Very well adjusted numbers. All throughout. So you know that the velocity of the fluid inside will be the same. So you are asking me indirectly. First question में velocity at d. is correct. PB, 1 second, wait. PB is 4.14 into 10 raised to 4 Pascal. 4.15 into 10 raised to 4 Pascal. PC is 6.4 into 10 raised to 4 Pascal. To find out the pressure at B, apply Bernoulli's equation at A and B. I don't mind. Anywhere. Pressure at A plus half rho V square is 0, potential energy is 0. Pressure at B plus half rho V square is 10 square. How much did you calculate velocity inside the fluid? 10 square plus height will be 1.5 h rho. Specific gravity of the liquid will be 900 into G. See if you are convinced. Pressure at A will be P naught. Why did you take kinetic energy here to be 0? Area of cross section is large. Why are you taking potential energy 0? You are taking that as a reference line. So when you are taking potential energy here, you take rho g h rho g, 1.5 into rho into g. 0.9 is the specific gravity. If I solve the problem in CGS units, density of the liquid would have been 0.9. But you are solving the problem in SI units. So 0.9 divided by, in the sense 0.9 into 1000. So becomes 900. Now calculating PB, atmospheric pressure is given as 10 to the power 5 Pascal. PB plus half 900 into 100 plus 1.5 into G is 10, 15 into 900. Remaining simplification, I leave it to your judgment. PC, PB 4 point. PC, how much are you getting? PC 6.4 into 10 raised to 4 pascals. PB you will get 4.15 into 10 raised to 4 pascals. PC you will get 6.4 into 10 raised to 4 pascals. PC I leave it to your fine judgment. After the lunch break, we'll continue with the problems on this subtopic. Hey, pause. Pause this. Listen to the terminology. A mercury manometer is connected as shown in the figure. The difference in heights delta H is equal to dash. Here you have got density of mercury. You have got mercury, right? D is this distance. D is this distance. Rho is the density of the gas. Options given are delta H is rho D cot theta by rho Hg, rho D tan theta by rho Hg, rho D sin theta by rho Hg. And the last option is none of these. And the last option is none of these. Think carefully and solve the problem. Not a very easy problem. Now you take this point as 1, this point as 2. This height I will take as h1. This height I will take as h2. H2 will be till here. So delta H is H2 minus H1. So obviously P1 plus half rho V1 square plus rho G H1 equal to P2. Do one thing. Take this height to be H2. This will be delta H. Both heights you are taking from the same reference line, so that potential energy expression will become easy. If not, here I will have to take H2 and delta H minus P2 plus half rho V2 square plus rho G H2. You are taking this as the reference line, so this is rho G H1 and this is rho G H2. Agreed? What is the advantage of doing that? Watch out for it. P1 is of your requirement plus half rho V square plus rho G H1 should be equal to P2 plus half rho V square plus rho G H2. Why did you take velocity to be the same at both the points for the fluid? Same area of cross section. So now life becomes simple. P1 minus P2 is your requirement. This gets cancelled. Rho G H2 minus H1. Pressure difference is delta H into rho of Hg into G. See if you are convinced by this. The pressure difference at 1 and 2 will be delta H into density of mercury, not the gas. Delta H is that of mercury. So delta H into density of mercury into G. This will be rho G H2 minus H1. Can I call it to be d tan theta? Why are you asking me that at the first place? If they are equal, don't you think I would have written 0 here? Huh? You're confusing me. Now, in one of the questions, Iridov is asking, this is a horizontal pipe. Water is flowing this way. You take a point 1 and point 2. Pressure at 1, same speed. Pressure at 1 is greater than pressure at 2, less than pressure at 2, equal to pressure at 2. Cannot say. Pressure at 1 and pressure at 2. Will they be equal? Will it be greater, lesser? Same objective we gave here as well. Louder. Why? No. Consider a small cylindrical element like this. The cylindrical element of the liquid is taking a turn. So here the pressure P2 should be greater than P1 to provide P2 minus P1 into area of cross section provides the required centripetal force. P2 will be greater than P1. The tube is not in the vertical plane, it's in the horizontal. Tube is in the horizontal plane. 1 and 2 are at the same heights. Right? Make a note of that, that's also important. Can I rub the left part of the board? Listen, a conical container of radius 1 meter and height 5 meters filled completely with a liquid. There is a hole at the bottom of the container of area pi into 10 raised to minus 3 meters square. Right? You will take G as 10 meter per second square. Find the time taken to empty the conical container. Find the time taken to empty the conical container. Find the time taken to empty the conical container. Time taken to empty the conical container. When you are saying 1 second, you are telling me the time taken to empty, or you are asking me 1 second to solve that? How much? No. No. Do it again. I didn't ask you to whistle. Who is that? Finally, you have learned something properly. My friend didn't like the sarcasm. He's making faces at me. You asked 1 second of a time to tell me this answer.
I promise you, sir.
That you will not disappoint me. So
I
what is the
just
final?
have to finish the.
Okay, finish. I'll give you 10.
Thank you, sir.
Either way, neither am I in a hurry.
Sir, so we have closed it completely.
Yeah. A1 V1 equal to A2 V2. A1 V1 is equal to A2 V2. Let me consider this to be at a height of h. Small h, you take y, anything of your choice. Right? Here, small a, pi into 10 raised to minus 3, root over of 2gh,
800 seconds.
200 seconds.
So, sir, 200 seconds, and I know 200 seconds, but I read it as 800 seconds. Sir, it's 18 seconds.
Right. Okay, you get the credit. Relax. Pi into h tan theta whole square. Velocity will be dh by dt. This step is the most crucial step. You get this, you get the answer. Remaining is called simplification. Area of cross section of this is given. If it is at a height of h, now why is this problem given for you? For you to understand that velocity is root over of 2gh irrespective of the shape of the container. Problem with you is you will close your mind to the fact that only for cylindrical containers velocity is root over of 2gh. Students repeatedly ask me this doubt, sir, only for cylindrical, they take it for granted that root over of 2gh applies only for a cylindrical container. Did I ever tell you it is only for a cylindrical container? Yeah. So velocity at a height h, the velocity will be root over of 2gh. Now, what will this radius be? H tan theta, because this will be h. What will this radius be? H tan theta into the velocity with which it is coming down is minus dh by dt. Now here truncated, people argue that h should be from here till here. They say this is tan theta, this, their requirement is small h should be till here. Small a is very small when compared to capital A. Now balance simplification, look at the way you people are looking at me. I'll help you out with one calculation, pi can be cancelled out. Right? dh by root h. At least finally you people have learned to say thanks at the right time. It took you so much of a time to learn that. dh by root h. No, there is a h square here which I am forgetting. I'll have h square here. H square. Right? H square dh by root h. Remaining all are constants. This will be dh I kept there means it will be 10 raised to minus 3 root 2g by tan square theta into dt. You are going from initial value of 5 to 0. Obviously, with this negative sign, 0 to t, balance I leave it to your judgment. It will be 200 seconds. Values are properly adjusted. You don't need to worry about the simplification beyond that, but do the simplification. By the way, tan theta is equal to 1 by 5. Tan theta is equal to 1 by 5. Don't ask me how, that's the magic. Right? This will be small here. H will become, for it to completely empty. You are asking me what is the time after which it gets emptied. That means the same point. You are not taking this to be small. You are taking it to be coming till here only, not till here. Assume that to be small. Small. This area of cross section is small, so even this will be small by similar triangles. That approximation they will want you to use quite frequently. Chapter is actually over. We are spending time with a few problems. Right? The theory of the chapter is over. Because we have time, I am solving problems on the tougher side. The next problem will be really tough. Now, listen. This integration you will be able to do. Hello. Hello. No, madam, not required. Pest control वालों को मैं reference बता. They'll first call up and they'll say trained marketing person. First they'll say, do you need anything, any requirement for pest control? Suppose we say not required. Can you give us any reference? I will give phone number of people to them who need pest. Okay, yeah.
So I think we sell those phone numbers to other companies. So you would have given one page of answer. No. Yes.
Now, before I go to the next problem, one small, very silly thing. There is a cylindrical hole, cylinder with a hole here. You have a tap here. What is the maximum height? H maximum. Pardon?
He's asking all the questions.
What is the maximum height? Liquid is flowing inside, liquid is flowing out. What is the maximum height? Now understand the logic. If this rate of flow is greater than the rate of outflow, then the height will increase. Suppose if this rate of flow is greater than the inflow rate, height will decrease. So maximum height will come when inflow is equal to outflow. Rate of inflow, if it is equal to rate of outflow, it will be H maximum. So he will give you the rate at which it is coming in. Equate it to rate at which it is coming in will be some number. Now equate it to small a into root over of 2gh. Rate of inflow equated to this. Will I get the height h? That will be the maximum. Right? Now, this has got nothing to do with the next problem that I am going to deal with. But listen to the next problem. You have a container, cylindrical container, in which there is a small hole at the bottom. So, you know the velocity of the flux. Yes or no? What is the velocity? Root over of 2gh. Fine. We are all happy about it. So because of that, if the container is on a smooth surface, it will keep moving backwards because of the acceleration called thrust force. How much is that thrust force? You helped us out with the formula rho a v square, vr square, right? I know only instantaneous acceleration because as the height is decreasing, when this is going back, as the height is decreasing, when this is going back, the velocity is decreasing. So flex rate is decreasing, thrust force is decreasing, so acceleration is decreasing. Mass is decreasing. Yeah, you will take that also into consideration. They asked for velocity of this container by the time it gets emptied. Velocity of the container by the time it gets emptied. Now, listen to this part. You will try this. This container is on a smooth surface and there is a hole here. Initially, height of the liquid is h, area of cross section is a, filled with water on a smooth horizontal surface. A small orifice is made on the bottom of the bottom of the container. A is much lesser than capital A. The tank recoils. Find the speed of the tank. Write down the last line. Find the speed of the tank in meters per second. Find the speed of the tank in meters per second. Find the speed of the tank in meters per second when it gets emptied. When it gets emptied. When it gets emptied. In the bracket you will write mass of the empty tank is negligible. Mass of the empty tank is negligible. That means you will take only mass of the water. In the bracket you will write mass of empty tank is negligible. Mass of the empty tank is negligible. Mass of the empty tank is negligible. Initial, no, mass of the empty container is negligible. Water area, height, volume, density. Density of water you know, height is given. Problem is a good one, give a genuine try.
Earlier we learned the formula root 2gh for the relative velocity for stage one. Here,
Root 2gh is with respect to the container.
always, because here my doubt was like this exerts a force on the container that causes it to accelerate. Because of that acceleration, won't the relative velocity of that fluid when it goes out change with respect to the container?
Relative velocity, where will it change? With respect to ground, it will change. Height will change, hence relative velocity will change. You people are trying the problem? Should I wait? 1 second or more than that? First of all, calculate the time it takes for it to get emptied. How much is the time it takes to get emptied? Capital A by small a root over of 2h by g. If you people have done this calculation, incidentally this will turn out to be capital A by small a.
So we are supposed to find the final velocity of
How much? How much is that? How much is h? H is 5 meters. Substitute. How much is it? Is correct. 20 meters per second. Have a look at it. How much will you have the thrust force on it? Thrust force is rho A V square. A is the area of cross section of this. Yes or no? That's what you told me then. Right? V square. I assume that at some instant of time the height is small h. In a short time interval dt, mass into dV by dt is rho A V square. The thrust force on it should be mass into dV by dt, yes or no? How much will be the mass in that short time interval dt? Rho capital A into small h into dV by dt is equal to rho small a 2gh. In that short time interval, after time t, in a short time interval dt, this equation. Here technically I should write after time t, in a short time interval dt, right? Rho ah into dv by dt is this. Rho gets cancelled out. Capital A, h also gets cancelled out. Capital A dv is equal to small a by capital A 2 times dt. Where did I forget g? It seems there is a g here. Balance, I leave it to your fine judgment. Initial velocity is 0, 0 to t, 0 to v, 0 to t. T will be capital A by small a. Huh? 20 meters per second.
So when I got that, I got confused because I thought I made a mistake. A by A is capital A by A, both the currents and the flows. Very confusing.
and I think I like this chapter more than properties of solids
All over first year we give importance to likes and dislikes. Second year, slowly, step by step, when do we know that the student is growing? When they stop giving importance to likes and dislikes. Right? Second year, mein, what will you start giving importance to? Which chapter gets how much weightage? Ironically, the most insipid chapter will be modern physics. Information for the sake of information. But that's the most scoring chapter. Most scoring chapter. The single unit from which 17% paper this year in JEE mains is from modern physics. Just imagine. 1-7. Right, 70%. I'll leave all the chapters directly teach. If 70% paper is from modern physics, why will I teach you all these topics? Dump everything, teach modern physics right from start till the end. Mechanics got 30% weightage. Heat and thermodynamics got 10% weightage. Fluids, mechanical properties, waves, all this got 15% weightage. Optics got 10% weightage. Modern physics got 17% weightage. And electrodynamics got 30% weightage. Pardon? 30. Now, why does the total go beyond 100%? Because they have taken the averages for all the papers. Some papers they didn't ask questions from certain topics. Some SHM they didn't touch in 1 or 2 sessions. 1 or 2 sessions they touch. So you add SHM and waves or not, we don't know. If we add, the total percentage goes beyond 100.
So we are still going to study the most scoring chapters.
Overall, second year syllabus gets 60% weightage. Overall, second year syllabus gets 60% weightage. Keep that in your mind. This diameter is 8 millimeters. This is located at a height of 1.25 meters. Nozzle diameter is 2 millimeters. The plunger is pushed with a constant speed of 0.25 meters per second, taking G as 10 meter per second square. Listen, here the piston is being moved with a speed of, consider a horizontally oriented syringe containing water located at a height of, this is water, at a height of 1.25 meters as shown in the figure. Diameter of the plunger is 8 millimeters. Diameter of the nozzle is 2 millimeters. Plunger is pushed with a constant speed of 0.25 meters per second. Find the horizontal range of the water stream on the ground. Find the horizontal range of the water stream on the ground. Find R. Find R. No, but not required. He played a very cheap trick with you people. All you had to do is A1 V1 equal to A2 V2. You know this area? You know this velocity? You know this area? You'll know this velocity. Once you know velocity, you'll know the range. All of you must have applied Bernoulli's equation, this, that. You applied, I like it. You have 15 minutes of a break. Now listen. This is of height h. This is of height h, 2 rho. This area of cross section is A. Two immiscible liquids are filled in a conical flask as shown in the figure. Area of cross section is shown. Area of cross section is shown. A small hole of area of cross section A is made at the lower end of the cone. Find the speed of the liquid flow from the hole. Open to air. This is open to air. Right? Find the velocity. Find the velocity. I want the answer in terms of H, small a, capital A. I want the answer in terms of H, small a, capital A. G also will be there, obviously. Velocity of the flux. You'll have to find the velocity of flux. Pardon? Small a, capital A, both. Say that again. What GH? Okay. No.
Total rejects by 1 minus mod a square by campus.
What GH? How much?
Sir, it's not 3 stages. Just 3 stages. So, this capital name
You will take this particular point as 3, this particular point as 2, this particular point as 1. Here the density is 2 rho, right? What will the area of cross section here be? That's why it wrote 16, it seems. If I take the velocity of the fluid to be V here, AV is capital A into velocity at 2. Velocity at 2 is AV by capital A. AV by capital A. What will be the velocity here? AV by 4 times capital A. What did I apply? A1 V1 equal to A2 V2. First of all, I am applying Bernoulli's equation between 1 and 2. Pressure at 1 plus half rho V square is equal to pressure at 2 plus half rho V2 square plus rho GH. Yes or no? I am taking this as the reference line. This will be rho GH. Pressure at 2. Now, pressure at 2. 2 rho GH, right? 2 rho GH, right? And half of here also it will be 2 rho. Here also it will be 2 rho. Pressure at 2. Pressure at 1 also will be 2 rho. Pressure at 1 plus half 2 rho V square. V2 will be how much? AV by capital A. This is my first equation. See if all of you are convinced.
So, E1 plus half V square, I don't think this is 1.
This is 2 rho. So velocity coming out will be for 2 rho. Now apply Bernoulli's equation to point 2 and point 3. Pressure at 2 plus half. Here point 2 I am taking just inside this. Rho into AV by A whole square. I am taking this as the reference line. Will be equal to pressure at 3 plus half rho AV by 4A whole square plus rho GH. This is my second equation. You are taking point 2, same point 2 when I am taking with point 1, I am taking just inside this liquid. Same point 2 when I am taking at point 3, I am taking just inside this liquid. So I'll take the densities here to be rho, while here I'll take the densities to be 2 rho. Hmm. It can, nothing wrong. But here, why are you doing it then? To maintain the same streamline. To maintain the same streamline, I am taking the second point inside this liquid, third point inside this liquid. Now simplify, make it very fast. This is the answer that you are supposed to get. V, if you simplify from these two, this will be 3GH upon 1 minus 17A square by 32A square. When did we promise you that the answers will be beautiful? Above all, beauty lies in the eyes of the beholder. Try to see beauty in that answer, JE will become easier. There will be a day, not very far off, when we will draw circuits like this. And we'll ask you for equivalent capacitances and equivalent resistances. I always tell the students, beauty lies in the eyes of the beholder. Look at the circuit with passion, you will be able to solve it. To find out, this is their standard problem in capacitors. Such type of circuits, then we'll draw cubes. Then we'll draw cubes and we'll tell you each of the side has a capacitance of C. Now there you tell me the circuit doesn't look beautiful, I'll be helpless. Beauty lies in the eyes of the beholder.
So this is it's a beauty that the other one is 7. You can convert it.
So 17 and 32 are your unlucky numbers?
Sure.
Need not. So now this answer looks beautiful to you? Now can I rub the board? Mm-hmm. Can I rub the board? Now listen. This is a container with a hole at the lower bottom, kept on the top of a table, Height of the liquid is h. Height of the stand is h. This distance is also h. Listen to the question. 4 meters. Cylindrical vessel of height 4 meters and area of cross section 1 meter square. 1 meter square. Filled with liquid rests on a stand of the same height h. It has a small plugged hole near its bottom. When plug is removed, the liquid starts to come out. Till here is it clear? Write down the next line. Find the volume of liquid collected. Find volume of liquid collected in the vessel shown on the floor. Volume of liquid collected in the vessel shown on the floor.
How long is
1 second, write first. Right? Listen, he tells you, do not assume that the liquid falling here will flow into this. Do not assume that the liquid falling here will flow into it. Directly it should fall into the vessel. Find the volume of the liquid collected in the vessel. Very politely he is asking me the hint for the problem. So nice of you. The left end of the vessel is at a distance of h.
Wait, wait. It's just how is liquid clear the capital in terms of weight.
By the way, just out of the way, this problem you will have to solve. When you told me that you dig a hole here, you told me range will be maximum, yes or no? At a height of h by 2, you told me range is,
Maximum.
what is the formula for range? Am I right?
Yes.
See your notes and tell me yes or no. Right? Now, height is h by 2. 2 root over of h by 2 minus h square by 4. 2 root over of h square by 2 minus h square by 4. 2 root over of h square by 4. By the way, our maximum will be h. Just for your information, where you have calculated this, make a note of this also. Now, why are you telling us this here? That's the hint for this problem. You have 5 minutes. But here, don't directly use that h because this is kept on a table. Here, R maximum will not be h.
Oh, the table also we can take at this.
Will you solve the problem or should I? I am waiting.
We aren't even the width of the vessel.
One meter.
That is width of this. He is asking width of this vessel. Fine. Cash price of 10 bucks for anybody who solves. USD no. One Cadbury chocolate here 10 bucks. I'll give you 10 bucks. Not I'll give you 10 bucks. Whoever solves. By chance you people are not able to solve, I will solve it. Implies I get the 10 bucks each from you. Come on. Fine, I'll give you one hint. This will make your life simple. See, this vessel is large, implies you don't need to worry about whether it falls here or not. It will for sure fall in the vessel, the first part of it. Right? For sure it will fall into the vessel. This part you don't need to apply limits. Now I made your life simple. So I cut short 10 bucks to 5 bucks. Volume. 3 meter cube is correct. You get your 5 star. It will come. We'll order. Nearby, where do you have a shop? Me? Town. After the class, you'll get your prize. The others, make it fast. Come on. Oh. Is it? 3. Fine. Your friend is bargaining a 5 star for you. It's okay. You will also get a 5 star. There is one shop here. If I see that clearly. I don't know if you'll get 5 stars. It appears more like departmental store. The departmental stores you'll get 5 stars. It appears like a departmental store. I don't mind. He wants me to trade the chocolate for something else. But you should not say no for that. I'll draw 5 stars on your hand. I said a 5 star.
So I will need to watch it, sir. That is.
What do you mean you want to trade the chocolate for something else? You mean something like weed, smoke, so on and so forth? I thought you people are yet kids. Did I even ask you? It appears so. He doesn't want a chocolate. He's trying to trade it for something else. And that guy is saying, I don't smoke. That means only alcohol. Nah, weed. How is it that you managed to say so high? Good. Better don't learn about it. Okay. Okay. Basically, this velocity, pardon? Okay. Width of? You mean this one? Yeah, it's only about the range. Listen, this velocity is root over of 2gh. Listen. Range will be v into t, root over of 2gh, 2h by g. Right? Time of fall, the time taken for it to fall will be this. So this will be root over of 2h into h. This is the range. Do you agree with that? The collection of the liquid in the container will stop if the range becomes less than h. Range becomes less than or equal to h. 2 root over of hh is less than or equal to h. 4h into h is less than or equal to h square. H is less than or equal to h by 4. Sorry, capital H by 4. So h less than or equal to 1 meter, it will not collect into this. So till it comes to 1 meter, the water will be collecting in this. Total height is 4 meters. So till it comes to 1 meter means total this is 3 meters of a volume. That into area. This volume will get accumulated into this. Agreed? Now, there is one question from Mirido given as a solved example in your booklet, in your material. This generally I solve. but I want you people to go through this example on page number 26, illustration number 12. Page number 26, illustration number 12. It's a typical problem from Irido. All of you have access to the book. Per bench at least one book. Beg, borrow, steal. Page number 26, illustration number 12. Page number 26, illustration number 12. Beg, borrow, steal. Page number 26, illustration number 12. Not big, beg. Borrow, then steal. Huh? No, you'll have to see the solution. You'll not be able to solve it on your own. He'll probably bring. Once you people are done, share the book with them. Once you people are done, share the book with them. You have 5 minutes to complete this. Here we don't have an office boy. Office boy. Do we have any office boy whom we can send and ask him to buy chocolates? हाँ, one more booklet. बे जब ला रहे थे एक और भी ला सकते थे ना यार. हाँ? No, you people see he went and made arrangement for himself. You keep sitting, books will not walk to you. Hey, listen. Pause this. Pause this.